biggest application of the wireless power transfer. It is named SPS, Solar Power Satellite, or recently we call it SBSP, Space-Based Solar Power. So from 60s, from 70s, this is one of the hopeful WPT applications in the world. And there are a lot of very huge national projects, not only in Japan, but also in US, in Europe, and in China recently. So I'd like to introduce a review of the recent R&D status of the solar power satellite SPS in the world. So this is a brief introduction of the SPS. So this is a brief history, as I mentioned in the previous talk. Here, after the success of the William Brown's demonstration, Peter Glaser proposed the solar power satellite in my previous talk. So this is a conceptual image of the solar power satellite. Here you can see it's a very small satellite, but real size of this satellite, solar power satellite, is 1 gigawatt solar cells. And the size of the solar cell will be 2 kilometer diameter, and the power from the 36,000 kilometer above to the ground transmitted by the microwave. And for the microwave antenna, we need a 2 kilometer size of the antenna. Please imagine. So this size and power is quite huge compared to the current International Space Station or the current commercial satellite. But theoretically, we can build this huge satellite because there is no gravity in space. And theoretically, we can develop the 2 kilometer size of the antenna. And based on the Maxwell's equation, we can transmit over 90% beam efficiency wireless power from the space. So this is not a dream. This is not a science fiction. This is not a Japanese manga. But in the world, there are a lot of real R&D projects with a very huge budget in the world. And when we realize this solar power satellite, merit of this solar power satellite is very stable, CO2-free power station will be established in future. So if we put a solar cell, same solar cell on the ground, in the rainy day, we cannot, the solar cell cannot generate. And of course, in the nighttime, electricity cannot be generated. But if we put the solar cell in space, there is no night in space because there is no shadow as a night in our region in space, and the microwave can be transmitted without any attenuation absorption, as I mentioned in my first talk. So if we put the solar cell in space, named the solar power satellite, we can increase total electricity over 90% of the year, day or the other. And we can increase the total electricity, even if we assume the beam efficiency is 50%. It is demonstrated by the William Brown. So solar power satellite is huge, stable, CO2-free power station in future by help of the wireless power. So during this about 60 years, there are a lot of R&D in the world. And this is a detailed parameters. For example, designed by the JAXA, Japanese Space Agency, about 20 years ago, based on the phase transmission formula and the Maxwell's equation. When we put 1.293 kilometer diameter as a transmitting antenna in 36,000 kilometers above. And of course, we assume the 5.8 gigahertz. And at the receiver on ground, when we put the 2.4 kilometer size of the receiver antenna, and the beam efficiency is estimated, calculated to the over 96% as a transmitting efficiency from the antenna to antenna. So there is no assumption. There is no expectation. This beam efficiency is estimated, calculated by Friis transmission formula and by Maxwell's equation. So we can reach over 90% beam efficiency even at 36,000 kilometers. And additionally, we can assume the DC RF conversion efficiency to, for example, 76%. At the receiver, efficiency will be reached 35%. For example, this is an engineering problem. So about 30 years later, I believe we can reach this conversion efficiency as an engineer and totally efficiency from the electricity in space to the electricity on the ground reach over 50%. And additionally, there is no night and there is no rain attenuation. So electricity on ground will be increased about 7 to 10 times larger than on the ground. And we use phased array antenna with a very huge number of the small antenna to control the beam direction. So we estimated the number of the antenna at about a 2-kilometer antenna will be 20 billions. Of course, some professor and some engineer consider it's impossible. But please imagine, we can develop very small powered antenna as one element, and we put the same antenna and the same circuit in the area of the 2-kilometer, and totally, finally, total number will be reached at 20 billion. But it consists of the same small antenna. So, as an engineer, I'd like to ask you why you think it's impossible. It's only a size problem. So, as an engineer, there is no secret in this calculation. So, I believe we can realize this huge size of the phased array antenna and the huge satellite in near future. I think so. And in this system, solar power satellite system, we put a receiver in radiative near field friendly region, as I mentioned before. So we can reach over 90% beam efficiency, even in at 36,000 kilometer distance. So it depends on the size of the antenna, distance, and the frequency only. I will explain the detail tomorrow. But theoretically, we can reach over 90%, even in the 36,000 kilometer distance. And this is a same PowerPoint in the previous talk. And this is the first proposed solar power satellite by only one researcher, Peter Glaser. And at that time, parameter is very similar. Size of the antenna will be 2 kilometers. And at that time, this power generation will be 10 gigawatt compared to 1 gigawatt recent solar power satellite, 10 times larger than at that time. So size of the solar cell was very large, 6 kilometer diameter. And he adds the superconducting power line between the solar cell and the antenna. And here you can see 22,300 miles. It means 36,000 kilometers. So original concept of the solar power satellite is the same as a recent design of the solar power satellite. And through this about 6 years after the first proposal by Peter Glaser, there are a lot of interesting and strange design of the solar power satellite in the world. For example, JAXA, Japanese Space Agency, and this is the other space agency in Japan, designed this strange shape of the solar power satellite. And China is designing these two strange type of the solar power satellite now. And of course, NASA, ESA, European Space Agency, designed these solar power satellites. So now there are a lot of different solar power satellites in the world now. And this is the explanation of the significance of the solar power satellite. Now I explain we can realize a future stable solar power station without any carbon dioxide. It's most important. But if we can build over kilometer size and over 1,000-ton satellite, we will get the very excellent space development technology, and we can move to the space immigration or to develop the space colony, like a Japanese animation Gundam or the other. So in far future, a few hundred years later, we can immigrate the Mars or Moon, we can immigrate the space colony, etc., based on the large satellite technology. But I suppose you cannot wait this solar power satellite and our dream, even within 30 years later, because now world economy is not good in the world, and especially in Japan, economy is become weak and weak. So we cannot wait the future dream. So in my previous talk, I showed you the new business as a game-changing technology of the wireless power. So these three stages, WPT business within a few years, and future power station without carbon dioxide in 30 years later, and future space immigration a few thousand years later, are based on the same radiative WPT technology. It's very important. So our WPT technology can solve this problem on the Earth, population, energy, or global warming, to apply the space technology. So the keyword we propose, we change our mind from the closed Earth system to open space system in near future with help of the wireless power. I think so. And key technology of the solar power satellite and the SBSP classified into these four big requirements. Of course, we need a very cheap economical launch system. Of course, we can expect the Elon Musk or the Jeff Bezos, etc. But to launch 10,000 tons satellite space segment, we must expect economical launch system. And additionally, when we build or we maintain the huge space segment over kilometers, we need a technology of the construction or maintenance technology in space. And additionally, power management in space plasma is very important. Of course, when we generate 1 gigawatt in space, as you know, space is not in vacuum. Space is in a very weak plasma. So in plasma means it involves a plus and minus particles in space. So in plasma, plus and minus particles, and when we add very high voltage to reduce resistance loss, unfortunately, plasma will be broken by this high voltage. So power management in plasma is very important additionally. And of course, wireless power transfer technology is most important, I think. So of course, you know, future technology named the space elevator or orbit elevator. And if we realize this space elevator, of course, satellite in geostationary orbit 30,000 kilometers above and the ground will be connected wirely. So if space elevator will be realized before the solar power satellite, we don't need wireless power. I agree. But I think compared to the space elevator, SPS will be earlier. So we need a wireless power transfer technology based on the WPT business or the advanced system. And this is a comparison of the scale of the space structure, as I mentioned. Recently, we have the 10-meter size normal satellite and a 100-meter size of the International Space Station. And one order higher, it's a solar power satellite. And plus one order higher, we can build space colony. I think it's only a scale problem. So as an engineer, I believe we can do it. And from here, I'd like to introduce a recent SPS R&D in the world. First of all, I'm Japanese, and I will introduce a Japanese SPS design. And this is the first Japanese SPS, and designed in the 90s, about 30 years ago. And at that time, we adopted silicon solar cell and microwave tube, crystron, or FET devices. It's a 30 years ago technology. And we put a kilometer size solar cells here, and we put a microtransmitter here. And the design of the weight was 2,000 tons. It's a first Japanese design. And the recent design of the solar power satellite in Japan is designed in 2004 by JAXA. And here you can see it's a very strange shape. We separated the solar cell and the microwave transmitting antenna here. And additionally, we add the mirror as a reflector and a concentrator of the solar ray. And with change of the position of the mirror and solar cell, we control the solar ray in every time, even in the one day, in the night time on the ground and the daytime on the ground. And with help of the change of the mirror position, we keep a stable power generation. And by help of the separation of the solar cell and the microwave antenna, we reduce the heat reduction system. So this is a JAXA design. And this is one part of the Japanese solar power satellite. And based on this design, we developed the demonstration of the solar power satellite 25 years ago. This is a movie of this demonstration. Inside this box, we put a microwave transmitter, and outside of this microwave system, we put a solar cell and a microwave antenna here. And we control the beam direction from transmitter to the receiver. Here you can see the turn on the right. And here it's a demonstrator of the solar itself. And we control, here you can see we control the beam direction. So this is a Japanese trial as a demonstration of the solar power satellite 25 years ago. And this is the detailed parameter. I skip it. And the other design was carried out in the other space agency, USEF. Recently, it is renamed as J-Space System. And this is a very simple solar power satellite. Once we put the solar cell behind the transmitting antenna, and we put a very long wire to keep the position of the solar cell satellite. So there is no power, there is no position control system, and there is no additional superconducting power line, etc. But compared to the simplest design, solar ray cannot keep the same power on the solar cell because this satellite moved to everywhere around the Earth. So unfortunately, this power changes day by day. But totally, compared to the solar cell on the ground, we keep a very high power in space. This is a Japanese design, and this is an expansion design with combination of this part. And based on this design, recently in Kyoto University mainly, we carried out some space experiment. So as I mentioned in the previous talk, this is the world first rocket experiment in Japan. My boss, Professor Hiroshi Matsumoto, carried out this rocket experiment. And we adopted a mother and daughter rocket system, and we transmitted microwave power to estimate the counter effect of the space plasma by this high power microwave here. And this is a movie, it's the same, so I skip it. And 10 years later, success of the first rocket experiment Minix, my boss, again carried out the second rocket experiment named ISI MET. But in this ISI MET experiment, we adopted phased array antenna to control the beam direction like this. And to change the beam direction is very important to estimate the counter effect of in the space plasma. So this is a world first and only one demonstration of the WPT in space with the help of the beam controlling antenna. And this is a movie of this rocket parts and rocket experiment. Here you can see a lot of small antenna element, and it's a phased array antenna. And it's the same system as the Minix, mother and daughter rocket, and in the daughter rocket, we put a receiver. And this is a real rocket launch about 30 years ago. And this is an image of the computer graphic 30 years ago. So we transmitted the microwave power in consideration of the in consideration of the he is a young Professor Matsumoto. So when I was a master course student, I joined this experiment. And he is Professor Kaya, as I mentioned in the previous talk, and they are young researchers in Japan. And in parallel, not only in Kyoto University, but in the Japanese Space Agency, ISAS, they designed the small solar power satellite demonstrator named SPS-2000. This is a very simple and small demonstration model designed by the all Japanese researchers. And they expected this solar power SPS-2000 will be launched 2000. But now we are in 2025. Unfortunately, there was no chance to launch this mid-sized solar power satellite in Japan. And in Kyoto University, we designed the other small solar power satellite, not to the grand WPT, but to the small satellite in space WPT satellite named the PowerSat. So this is one example, and there was no real experiment in Kyoto University and in Japan. And based on these previous experiments, and recently we have a big project supported by the Japanese government, METI. METI is a Ministry of Economy, Trade and Industry, and not a space agency. But as a business spin-off technology, METI is expecting the wireless power and the solar power satellite. And from 2009, we started this R&D project supported by METI in Japan. And through this, about 20 years, I am a chair of this national project of solar power satellite. And we classify this METI's project phase 1, 2, 3, and additionally 4. And until the 2014, we developed a very good and high efficiency phased array antenna with a novel designed gallium nitride hem. And we demonstrated the 50 meters WPT demonstration at distance. And with help of this developed phased array antenna in phase 2, we carried out the drone WPT demonstration. This drone was bigger than my student drone. Because in this project, we had a very big budget compared to my university budget. So distance was at 30 meters above, and we transmitted 1.6 kilowatts. But so before a question, I'd like to mention efficiency from transmitting antenna to the receiving antenna is very poor because receiver as a drone was very small. But we can support additional power to extend the flying time in this drone. This is a phase 2. And phase 3, we revised this phased array antenna with help of the good amplifier technology. And for the phase 2 satellite experiment, phase 4 satellite experiment, we carried out a vacuum radiation experiment and a demonstration at a 7-kilometer distance. I'd like to introduce in order. So this is the first demonstration at the end of the first phase 1. We developed this thin, very low cost and a very high efficiency phased array with a gallium nitride MMIC. And we carried out a beaming demonstration at a 55 distance away. This is a detail of this developed phased array antenna. So this phased array antenna is very thick phased array antenna. Originally, this thick of the phased array antenna was 30 centimeters in previous demonstration. But in this experiment, thickness of the phased array antenna was only 2.5 centimeters. So it's very lightweight and a very good phased array antenna developed in the 2015. And in parallel, we had additional budget at the time. We developed a magnetron phased array to reduce the cost and to increase the transmitting power. And in this parallel experiment, we carried out a 500 meters demonstration by the magnetron phased array. Technology of the magnetron phased array will be described in the on Wednesday in this Gian course. And this is a detail of the second demonstration at the last of the phase 2. So this is a drone with rectangles, rectifiers. And here you can see a drone with a rectifier. And it's not clear, but here we put a receiver here, phased array antenna. And from the transmitter to the flying drone, now just here you can see here is a drone over the 30 meters away, above, and there was a microwave power beam, and this drone could fly with help of the wireless power. Not only wireless power transfer, but we add the extra power by the microwave power. This is an excellent result in Japan at the end of the phase 2 at the 2018. And I skip this. And now we are in at the end of the phase 3. And last December, we carried out the long distance, 7 kilometers distance demonstration, the beam WPT from the flying airplane. We put the phased array on the body of the airplane, and this airplane fly at the 7 kilometers above of the receiver. And we detect the position of the receiver, and we control the beam direction from the 7 kilometers above. And this is a real developed phased array antenna at the bottom side of the airplane. And this airplane fly over the receiver, and we detect the position of the receiver, and we control the beam direction. And this is a movie of this demonstration about a half month ago, I don't know, half years ago. So this is the experimental team. I was not here because I'm a chair of the management committee. But my colleagues, young researcher in Kyoto University, joined it. And some of my students joined it, this development and demonstration. And maybe here and here, and I have to skip. So this is a computer graphic of this demonstration. So here you can see the flying airplane, and just over the receiver area, this airplane transmits the microwave power in short time. This is the inside of the airplane. There is. Yeah, here is a flying airplane with a demonstrator, and this is one part of the receiver. So efficiency was quite poor because we cannot put a large receiver area. We put only one small receiver at everywhere, and we check the beam form, and we compare the theoretical beam form and the experimental beam form, and we check the accuracy of the beam forming. So this is a very interesting demonstration, but the longest distance demonstration of the beaming WPT in the world. So this is a brand new experiment. And these phase 1, phase 2, phase 3 Japanese R&D of the solar power satellite were conducted based on this roadmap to the commercial solar power satellite in 2050s. And at first, phase 1, phase 2, phase 3, we succeeded in the demonstration. And now we are phase 4. We will launch satellite soon in this year. And this is a figure of the designed satellite, Ohisama. Ohisama means a warm sun in Japanese. And it's a very similar experiment by the 7 kilometers this demonstration in phase 3. And from the 450 kilometer altitude, we transmitted the microwave power to the detected exact position of the receiver. And this is a developing array antenna. It's very similar to the airplane experiment. But now we are waiting for launch order. So I expect so we will launch it very soon from Japan. So this is our Japanese status. And here I'd like to introduce world status in US, China, Europe, and additionally in India, very briefly. So this is SPS design in US. Of course, Peter Glazer and William Brown were the US citizens. And so NASA and the DOE, Department of Energy, was Department of Energy design in the end of the 70s. This is named the reference system. And through these 20 years, there are some kind of the solar power satellite design in US. And recently, this is a brand new SPS design in US named SPS Alpha. It's very strange shape of the solar power satellite. And this is designed by the only one people, John Mankey, a very famous solar power satellite researcher in US. And this is a summary of the recent R&D of the solar power satellite in US. And recently, Air Force or Naval Research Laboratory carried out the WPT demonstration and the design of the solar power satellite. And the big wave of the in US of the solar power satellite is one is a SPIDER, space solar power incrementable demonstration and research. They got a $1 billion budget for this SPIDER experiment. And the other big wave is a demonstration in Caltech, California Technology Institute. And they got the same $1 billion budget from industry, and they carried out the demonstration in space named MAPL. And the other, my friend in DARPA, carried out the laser power transfer at over 8 kilometer distance in this May in US. And this is a picture of the Caltech satellite experiment named MAPL. And this was carried out in the end of the 2022. And they carried out the demonstration in space about the developed MAPL microwave transmitter and the solar cell combination system. And additionally, they transmitted microwave power to the ground. But they don't use a phase array system in this experiment. So I believe Japanese Ohisama satellite is a world first WPT demonstration from the satellite with help of the phase array antenna. And additionally, we can transmit power wirelessly by lasers, not by microwave. So DARPA, Japan, US Budget Foundation, carried out the laser power transfer at 8 kilometers distance, and transmitted power was 800 watt as a laser power. And based on the Friis transmission formula, if we choose optical laser power transfer, we can reduce the size of the antenna and we can increase the efficiency. So even at 8 kilometers distance, they receive enough power to cook the popcorn, they say. So this is a very brand new demonstration by DARPA in US. Sorry, data is different. 2025 May. So now in US, there are a lot of interesting demonstrations. And in Europe, for the Net Zero Society, they have some demonstration, and they have some research project in Europe. This is one example of the demonstration in Europe. So in Munich, 3 years ago, they demonstrated the in-room beaming type WPT by supported by the New Zealand startup company Emerald, and they succeeded in the beaming WPT demonstration in front of the European Space Agency colleagues. And in UK, England, they designed very strange shaped solar power satellite named Cassiopeia, and they carried out the development of this Cassiopeia solar power satellite in UK. And this is a startup company to promote solar power satellite itself, named Space Solar, not WPT startup. This is a startup of solar power satellite. And he is a co-founder and co-CEO of this company, Martin Sauter, and I'm a technical advisor of this company. And they are developing the demonstrator of the Cassiopeia twisted solar power satellite, and the result of the measurement was published in the proceedings of the IEEE WPTC 2025 in Roma. And in China, this is the last country most active WPT solar power satellite research. In China recently, they designed some kind of the solar power satellite. And now, in my understanding, there are some research university to promote the solar power satellite in Chongqing and in Syria, especially in Syria. So this is not a computer graphic. So this is a real picture in their campus. They built 7 meters height tower, and they built a demonstrator of the solar SPS Omega they designed, and this involved solar cell and microwave transmitter, and from the top of the tower, they transmitted microwave power. So this is ongoing program. When you visit the Syrian University campus, you can watch this tower. This is not a cartoon. This is not a computer graphic. This is a real photo in Syria. And in Chongqing, they are developing the very big research institute outside of the Chongqing downtown. I visited there 2 years ago, and they employ a lot of researchers for the solar power satellite in Chongqing University. And this is their Chinese roadmap. And target is the same. In 2050, we will launch commercial solar power satellite. But within a few years, they will launch small satellite of the WPT demonstrator. Of course, compared to the Office Summer project, I've not heard any budget support from the Chinese government to them. But I suppose suddenly they will do the satellite experiment. And this is last figure in my lecture 3, Indian situation. But unfortunately, I don't know any information about the R&D of the Indian solar power satellite. But about 10 years ago, so your Prime Minister Modi visited China, and he discussed a lot with Chinese space agency And so at that time, he was interested in the R&D of the solar power satellite and the wireless power transfer. But through these 10 years, there is no advanced news. It's unfortunate. And sometimes I receive the news from the India, but there is, unfortunately, there is no real R&D project in India. But if you are interested in the solar power satellite and the wireless power transfer in India or in NIT here, so please try to ask your Prime Minister to get a budget. So this is my talk last figure. So it's a summary of today's talk. So wireless power transfer can be applied not only for business, but also for the future power station without carbon dioxide. And additionally, our technology can solve our Earth and the human being. So with help of the wireless power, we can immigrate the moon, Mars, or space colony in far future. Please believe me, please trust me. So that's all my today's talk. So thank you so much. Yes, please. Please speak loudly.
Thank you for giving me opportunity to ask a question. Sir, you have explained your experiment that was taken in under research by you in Kyoto University, that you conducted experiment in three phases. What my attention got in second phase, that like you you placed many receivers and one aeroplane, like a transmitter on aeroplane, and aeroplane was like on a round trip. So my question is that have you got same intensity, beam intensity on all places of receiver antenna?
All places.
Yes, small antennas that you placed on ground.
Yeah. So of course, it depends on the theoretical limitation of the phase transmission formula, etc. And when we decide the aperture of the transmitting antenna and the distance and the frequency, it's easy to estimate the received power on the at the receiver. And at that experiment, receiver area is very small, and we cannot gather enough power. But if we put a large size of the receiver, it's easy to gather the transmitting power, and it's easy to increase the received power and efficiency. But due to the budget limitation, so we cannot develop the large size of the rectifier. And now world record of the WPT demonstration was 54% by the William Brown only. And the distance was only 1.7 meters. And if we expand, for example, in the 70s demonstration, even if we use a 26 diameter parabolic antenna and a 3x7 receiver, distance was 1 mile, and efficiency was only 8%. So this is one big problem and interesting engineering approach. So, but in Japanese experiment, unfortunately, we don't have enough budget to develop the large receiver or large transmitter. So efficiency was very poor.
Can you please point out the main observation that was come out from that experiment?
Yeah,
Please.
so as I mentioned, our aim of this demonstration was an experiment. This airplane experiment was a satellite experiment to check the beamforming technology, its accuracy or the limitation of the theory and the experiment. So at that time, at this airplane experiment, we measure the beamform itself, and we compare the measured beamform and estimated or calculated beamform, and as a result, we realize the theoretical correct beam by this demonstration. So next we expand this experiment into the space, because at the airplane experiment there are a lot of researchers very close to the transmitter inside the airplane. So if there are some troubles in transmitter, it's easy to check this transmitter in the airplane experiment. But next, there is no professor in satellite. So next time we will check. So only the wireless communication between satellite and ground, and we will check the longer distance beam-forming technology. And additionally, of course, we are the measurement of the counter effect of the plasma by the power beaming, like MINIX or the ISMS experiment. So this is our aim of the Japanese satellite experiment.
Thank you, sir. Thank you.
Yeah. As maybe you know, have a safety limit of the radio. In all radio wave, there is a safety level. And it is estimated by the lot of experimental result or the other. And so now, for example, at the microwave frequency, this safety limitation is a 10 watt per square meter, for example. And it means 10 watt square meter is not enough to carry the 1 gigawatt power beaming. So it's fortunate or unfortunate. So we increase the power density at the center of the receiver close to the 1 kilowatt per square meter. It's a real limitation of the safety, like some power. And but if there are some birds or human inside the hazard area, receiving area, so I don't recommend to stay for a long time. But only the one motion, 1 second, there is no problem. But so if we stay in hazard area, a little bit dangerous.
And it will also be effective on airspace also, because
Yeah, so it's a different problem of the, not mainly the human safety level, but also the wireless communication interference. So, but we keep the same beam in future. And so now, so we can avoid this beam by the airplane, I believe so. And suddenly they confuse so airline, and they go into the power beam. But airplane fly always. So only a few seconds or a few minutes, they will be inside the beam. And so as I mentioned, power, I don't recommend to stay inside the beam, but just a few seconds, a few minutes, there will be no problem. But we need more time to estimate the human hazard or the safety problem before the solar satellite.
will this experiment also leads to global warming, because iron will be also ionized and produce heat?
Yeah, of course. But so to ionize the plasma or to heat up the air or the other. So so based on the other knowledge by the satellite communication or the power beaming demonstration in 70s, so we consider there is no big effect to ionize the plasma or to create the ozone hole or to heat up more the atmosphere or the other. Power of the 1 gigawatt is very small compared to the total input power from the sun. So we consider effect of the microwave power beaming to the plasma, atmosphere, etc. is very small. But we need more research to check the effect, unexpected effect.
And there will be also free space power loss also.
So
So how will we
as I mentioned,
decrease
free
that?
space power loss is close to zero if there is no ray. But it's easy to estimate by the data of the wireless communication. And so in the microwave frequency, So we can estimate the power loss in the air or in plasma, etc. And in the microwave frequency, if it's a shiny day, so power loss is very, very, very small. Even in the very heavy rain, like a typhoon or hurricane, so power loss will be increased to 1 dB totally or the other, but it's negligible, I think so, compared to the beam efficiency between transmitting antenna and receiving antenna without any attenuation in path. So how to reduce the unexpected power outside of the receiver is very important. So, but by the natural phenomena, we estimated the power loss, real power loss in the air, in plasma, etc., is very small if we adopt microwave frequency. But if we increase the frequency to reduce the size of the antenna, attenuation in the air suddenly increases. Of course, at last, laser power transfer. It's like a solar power. So in the rainy day, attenuation is very huge, and we cannot apply the laser power transfer in a rainy day.
Okay, so this experiment have less efficiency in terms of raining and in these terms.
So this is not only a WPT experiment, but now there are a lot of satellite communication systems in the world, and they always estimated the air attenuation, rain attenuation, plasma effect, etc. by the information waves. So based on this, theory, based on this experiment, we have a database of the attenuation. For example, in my talk, I introduced rain attenuation data by frequency. So this is based on the satellite experiment, not a WPT satellite, wireless communication satellite. And we named it the very few loss frequency area is radio windows. So this radio windows is 1 to 10 gigahertz, and it's very low loss in the rain and in plasma, etc. So solar power satellite, we adopt the 5.7 gigahertz because it's in the very low loss frequency region radio wave windows. And of course, if you consider 2-kilometer size antenna is very huge, and we cannot do it theoretically. We can increase the frequency, but in this case, attenuation increases. So we choose now 5.7 gigahertz for solar power satellite.
Thank you, sir.
So, yes.